Hi everyone, this video is on a factor group of group homomorphism. It states let phi from G to G dash be a group homomorphism with kernel H. Then the cosets of H in G, G by H forms group under coset operation AHBH equals to ABH, and the group G by H is known as a factor group. Here the set is G by H, the cosets of H in G, and the binary operation is the coset operation AHBH that equals to ABH. Now we proceed to the proof. First we show that the coset operation AHBH equals to ABH is well defined. That means it is true for any choices of the elements from these two sets. Now AH and BH are sets, and a set can have more than one elements. So we can have more than one elements to choose from these sets for operation, and this operation is well defined means no matter what elements we choose from these two sets, the operation is always true. Now let AH1 be any element of AH and BH2 be any element of BH. Then AH1 BH2 equals to AH1 H3B, because H is a kernel, and for a kernel we prove that the left coset BH equals to the right coset HB for all B belongs to G. Then we must have BH2 equals to H3B for some H3 in H. So this is step. Then we have AH1 H3B that equals to AH4B, because H is a group, and by closure axiom H1 H2 equals to H4 for some H4 in H. And this gives us ABH4 by the application of associative property, and ABH4 it belongs to ABH. So we have for any two elements from the sets AHBH, when we operate them, we always get an element from the set ABH. So the coset operation AHBH equals to ABH is well defined. Also note that the coset operation was well defined only because of this property of H. For H, the left coset BH equals to the right coset HB for all B belongs to H, and this property is known as the normal property of a subgroup. We'll discuss this property in detail in another video of normal subgroups. Next we show G by H satisfies 4 axioms of group. For that, suppose AH, BH and CH be any elements of G by H. Now from coset operation we have AH times BH equals to ABH, and for any AB in G we have AB belongs to G. Therefore we have ABH belongs to G by H and G by H is closed. Next, AH BH times CH gives AB times CH. Apply associative property, we get A times BCH, and this gives us AH times BHCH, and this shows G by H is associative. Now because G is a group, there is an identity element E in G. So EH belongs to G by H. Now we show that EH is an identity element of G by H. For that, let AH times EH, and that equals to AH itself. This shows EH that equals to H is the identity element of G by H. Next, because G is a group, for any A belongs to G, its inverse A prime belongs to G. So A prime H belongs to G by H. Now AH times A prime H gives us EH that equals to H, which is the identity element of G by H, and this shows that A prime H is the inverse element of AH in G by H under the coset operation. So the set G by H satisfies all the 4 axioms of group under the coset operation. Therefore the set G by H is a group under the coset operation, and the theorem is proved.